Hi everyone, how are you guys doing today? Today we're going to actually start talking about some more physics stuff and kind of get a little bit more into it in depth, into some physics concepts, kind of the introduction into kind of some stuff and concepts and terms that we're going to be using throughout the year. So after this lecture today, you guys are going to be able to analyze motion of an object by using something called motion diagrams as a tool to, again, analyze that motion. And then you're going to be describing motion in terms of position, displacement, speed, and velocity. So these are some 4 terms that we're going to be talking about today as well. And then as we kind of go through things, I want you to kind of think about when you hear these words that I'm going to be mentioning, like speed and velocity, think about some stuff prior that that maybe in your life you kind of, talked about the speed of a car or like the displacement, distance, like how far something travels. So think about, if you would, stuff from the past that you can apply then to these new kinds of situations. Okay, so before we get started, I just wanted to kind of go through this concept here, just a little check to see from what we talked about last week, which was metric system, the SI system. And so the correct SI, which again is the metric system units for distance and mass, are. So which one, A, B, C, or D, if you think about it and kind of remember back, which one you think is the correct units for distance and mass in terms of physics and what we will use in the physics classroom? And you would be correct. The answer is D. All right, so starting off talking about physics and what we're really focusing on these next few months here is something called kinematics. And kinematics is just how we kind of look at objects, how we can describe objects. So mechanics, well, I guess let me go back to mechanics. Mechanics is a branch of physics that studies motion and the change of position. And there's 2 types of mechanics under physics, and that is dynamics and kinematics. Dynamics deals with like forces, like why objects move. So, for example, if you have a soccer ball that you kick in the air, the force applied to the soccer ball by your foot is something that we might want to study, and that would be dynamics. But then when we talk about kinematics, is how the objects move, describing it. That would be like, okay, so you kicked it with your foot. Well, we're not really worried about how it got in the air. We're wanting to know and describe how is it moving. So how high did it go? How far did it travel? Those kinds of things. And so like what was its motion? So that would be kinematics, and that's what we're going to be looking at. Excuse me, I have a thing. Okay, so we're going to be kind of starting with chapter 1 and kind of, we've already talked about chapter 1 a little bit, so we're going to kind of finish up with chapter 1 today, and we're going to get into a little bit of chapter 2 as well today. So our goal is to kind of introduce, again, those concepts about motion and kind of how it can relate to some mathematical principles that that you've had related to some basic stuff in the past. And, looking at motion here, all right, here we have a skier that jumps in the air, and this series of images of a skier clearly shows his motion. Such visual illustrations are a good first step in describing his motion. So if I were to ask you to kind of look at this and describe what's happening, so here he traveling pretty fast, right? Then takes off from the snowbank and kind of does kind of moves his body in the air and then lands. And so we can kind of talk about looking at that motion. What's the path that it takes? Is the motion in the X direction? Is it the motion in the Y direction? Is it in both directions? So again, kind of looking in, describing that motion. So you'll learn to make something called motion diagrams to kind of help get a better understanding of motion and being able to analyze those diagrams to describe what's happening with the object. And then this again is just kind of talking about, what do we describe or how do we measure speed, right? We use a speedometer to measure speed. How do we measure distance? Oh, we'll use a meter stick to measure distance. And so we're going to be looking at, talk about units in science, how we can convert those, things we've kind of done already, but we're just going to kind of continue to use those with our next topic here. Okay, so let's take a look at motion and what motion is. Motion is the change of an object's position or orientation with time. So here we have this this RV that's just driving down the road here. You can see nice straight line motion going down the road or up the hill a little bit. Here we have a ball going down the hill. Again, ball's rolling down a hill, down this incline. From the moment it's released to just before it reaches the bottom, this is a good place for a discretion on the start and the end motion. In other words, when we talk about position, we have to have a beginning point and a final point. So our beginning point would be up here at the top of the ramp or the incline, and then the final would be at the bottom. So along with motion, you have to, when we're talking about like the orientation, you have to know where the be able to reference it to something. In other words, you have to have some type of frame of reference. So like if I were going to ask you now if you are moving, so as you're watching this video, are you moving? And your answer could be yes, and your answer could be no. If the answer is yes, then that means that even though you're sitting down, you might be moving relative to like the sun because you're on the earth and the earth's moving, so therefore you're moving as well. Well, if the answer is no, then it's because it's in reference maybe to the table or the desk or the floor that you're on. So again, we have to have a frame of reference in order to measure our motion. So any measurement of position, distance, or speed must be made with respect to a frame of reference. So for example, if you're sitting on a train and someone walks by or walks down the aisle, their speed, how fast they're moving, with respect to the train is just a few miles an hour at most. Their speed with respect to the ground, though, is much higher. So if you look, respect to these people here, as he's moving, he's only going a few miles an hour, however fast he's walking. But if you were standing outside watching the train go by, right, he's going to be moving a lot faster because it's not only how fast the train is traveling, but we also have to include his speed as well. So again, depending on frame of reference. So this particle model that we're going to, like this diagram thing that we're going to be talking about, is a way to kind of simplify the motion of an object. Okay, so like for example, we have this car, and if this car is moving down or kind of moving sideways, I guess you could say, what we can do is say, okay, let's take the center of mass, and the center of mass is the single point at which you can concentrate all that mass, or center of weight, center of gravity, where you can concentrate all that weight. So when we're talking about this car, the center of gravity is right around the center of that object, so right around here, and we can kind of put it on the ground. All right, so you can see that we have the center of mass, all right, for this car. You can kind of see that it's evenly spread apart here, okay? And so what we do is we focus on, I guess you could say, the dot, so to speak, call it like a point mass. We look at the dot, and that's what we will analyze. So instead of like saying a car going down the road, you can think of like a dot going down the road, and that dot would represent the car because it's going to be a point mass. It's going to be that single, it's going to be all the mass of that car concentrated at one point. And just kind of a side note, your center of mass is right around your belly button area. And so if we could kind of shrink you down to just your belly button, where your belly button is, that would be your center of mass. And we're going to be talking more about center of mass later in the year. All right, let's go to the next slide here. So here's another kind of example of what I'm talking about. This, well, they call them particle models. I like to call them motion diagrams as well. So here we have a car moving down the road, and you can see that they're bigger spaced here, and now they're getting smaller space between them. Okay, well, if we take the same motion now and we put a dot, again, the center of mass for these is about right here, right? And so if we take and put a dot at the center of mass of the cars, right? This, instead of having the whole car, we're just going to focus on those dots. You can see that here are the dots down below. And so these are the exact same situations, but instead of analyzing the whole car, we're just going to analyze the whole car in terms of a point mass. And these numbers here would just show you kind of the frame that we're looking at. Okay. Let me get rid of those. And okay. Sorry about that. All right, so here's another motion diagram. We have a guy on a skateboard, a person running, and then we have a car moving as well. So which type of motion is in each diagram to the left? So if I were to ask you what's happening with this skateboarder, think about what's he doing. Okay, think about her. What is she doing? All right, and then think about the car and what is it doing. So if you were to describe the motion, what was happening, right, you can kind of tell me what you think. So take a moment and think about it. What is each one of those diagrams showing you? All right, so if we go to the next slide, we kind of have that told to us here. So these motion diagrams in one dimension show objects moving. So here we have again the skateboard. He's moving at a constant speed. She is speeding up. The car here is slowing down. So if I were to ask you, think about constant speed, which we're going to kind of focus on in this particular lecture, you can see that it's the same distance between him for each moment of time. So like if this was at 1 second or 0 seconds, this was at 1, this was at 2, this was at 3, you can see that he's covering the same distance in the same amount of time. So therefore he's moving at what we call a constant speed, has uniform motion. Okay, here you can see that she's closer together here. So like if this is, 1 second here, then 1 second between these two images, then 1 second between these two images, you can see that her distance is getting further apart, which means that she's speeding up. And then for the car, it's just the opposite, right? The distance between the two cars is greater. And then as you move and the time goes on, they get closer together. So that means that the car is slowing down. So again, if you were to do a motion diagram for these, you would just put dots at the center of mass of each one of these, and you can analyze the motion that way. So here we have a quick check. So here we have, again, two cars. Motion diagrams are made of two cars, of these two cars. Both have the same time interval between photos. Which car, A or B, is going slower? So think about, which car is going to be going slower. Again, think about the time between the cars is the same. So if the time between, so from here to here is 1 second, here to here is 1, here to here is 1, here to here is 1, here to here is 1. So which one would you think would be going slower? And car A would be correct. All right, again, if you think about it, the distance between here is a lot, which means they cover more distance, right, in 1 second. Here you're covering less distance in the same amount of time, so therefore it has to be going slower. Okay, here we have two joggers jogging along a track. The positions are shown at 1 second intervals. Which runner is moving faster? So again, here's A. You can kind of see the distance between them, again, 1 second, and here's B. All right, so runner A or B, which runner is moving faster? Give me a minute, think about it here. Not really a minute, but a few seconds. And the answer is A. Again, on the same scenario where, again, you're covering more distance in the same amount of time, so therefore you have to be traveling faster. Okay, here we go again. Two runners jog along a track. The times at each position are shown. Which runner is moving faster? So here again, you can kind of see the two joggers, and you want to know which jogger is going to be moving faster. The times at each position. So here is position 10, position 20, 30, 40, 50. You can see the times. So what do you think? Runner A, B, or both? And the answer is both. And again, even though this dot is here, you can see that they end at the 10-meter mark at 2 seconds, the 20-meter mark at 4 seconds. So they're both at the same spot at the same time. So they have to be going at the same speed. Okay, so we're going to get back to speed here in a little bit. But before we do, we want to talk about 3 things here: distance, displacement, and position. So distance is just how far you traveled, regardless of the direction. It doesn't matter, if you turned left and then you turned right and then you went up and down. It doesn't matter, all right? How far you traveled, regardless of your direction. And distance is a scalar quantity. And to represent distance, we use an x. Displacement is how far you are from where you started. It's where you are in relationship to where you started. So, and it is a vector quantity. And so the difference, again, between these two is one's a scalar and one's a vector. They both use x, regardless if we're talking about distance or displacement. They use x to represent distance and displacement. But the difference is that if you have a direction with it, then it's going to be displacement. If it's just how far you travel, they don't care the direction, then it's distance. And then position is where you're located relative to a reference point. So in other words, your position and your displacement can be the same. Okay, so it's where you're located, and you have to have a beginning and an ending point, so to speak. Okay, we're going to talk about position here in a minute. So when we talk about like a position and talk about located somewhere, a particle in space, one dimension is just in the x direction. Okay, and let me just say too that one dimension can also be only in the y direction. So when you think of a particle in space, it can be just a single x position or a single y position. So I forgot to put the y in there. 2 dimensions is an x and a y. So in other words, it's going to be like a 2-dimension could be like if you kick a soccer ball. I'm going back to the soccer ball here. If you kick a soccer ball, that it's moving in the x direction because it's moving downfield, but it also is moving in the y direction because it's moving up. So that would mean it's 2 dimensions. And then, of course, you've got 3 dimensions, which we won't really even get into, but I just want to kind of mention that as well. Distance and displacement. So what's the difference here again? So here we have a oval track, circular track. Here we have 2 positions, A and B. All right. If I go from position A to position B, and I go along the track there, I went 100 meters. That's my distance. But my displacement is how far I am from where I started. So if I start at A and I end at B, my displacement, how far I am from where I started, is just 50. Now, what if I went all the way around the track and back to A? So for example, I went on one whole lap. What would be my distance and what would be my displacement? Well, let's think about this. My distance, if this half right here is 100, well, then this half over here has to be 100. So then my total distance here would be 200 meters. So that would be my distance. But what about my displacement? If I start here, I go all the way around and I end back at A, that's my ending point. What would be my displacement if you're back where you started? Well, it should be 0 because you're back where you started. So you really didn't go anywhere. So your displacement would be 0 in that case. So now we're going to continue to look at motion, but now we're going to look at motion in a straight line. So you can kind of look here, we talked about motion kind of going around a circle. Well, now let's look at it in a straight line. And we're going to be talking about, again, that whole distance, displacement, and position here. So to specify position, we need a reference point, again, an origin, like something to measure it from. A distance from the origin and a direction from the origin. Again, will give you the displacement. So the post office defines the 0. So we decided, and it could be whatever, but we decided that the 0 was going to be the coordinate system, okay? So this cow is at a position of 5 miles to the left of the post office. So that's why there's a negative there. So with the cow being to the left, this is 0, like a number line, right? So this is 0, so these are the negative x values, these are the positive x values. So my cow is 5 miles in the negative x direction, so negative 5 miles away. My car, though, is 4 miles away, and it's the positive direction. Now, you might be asking me, well, does it matter which one you make positive and negative? And the answer is no, it doesn't. But it is, for cohesiveness, it's better to just use a normal timeline where you have the 0 in the middle, you have the negative to the left, and you have the positives to the right. Again, they can switch that up on you, and you could definitely switch it up too. But more often, it's just easier. What is just easier to kind of keep it the way it always has been. So the combination of an origin and its axis marked in both the positive and negative direction makes a coordinate. So I just want to and that's kind of what I just mentioned, is that this is like our coordinate here. This is the x direction. And so by placing the, again, post office at the origin, that's your 0, 0 mark, right? So this would be 4, 0. This would be what, negative 5, 0, those kinds of things. So now with time, I just want to kind of go through a couple of things because we all are familiar with time, right? Time is measured in seconds, hours, and minutes, but we use seconds the most. And when we talk about time, we need to label like each frame with some corresponding time. In other words, like what are we actually going for? Because if you notice here, we've got two situations that are the same, right? So if we're interested in the entire motion of the car, we assign this point, the time is going to be 0. So in other words, here we have the car's driving down the road, and then you notice at 4 seconds, it starts to brake, and you can kind of see the dots, those right motion diagrams, those dots are getting closer together. So this is the motion of a car that's going to be braking. If I were to ask you, well, what's going on from 0 to 4 seconds? You would say, oh, it looks like the car is moving at a constant speed or constant velocity because the distance between the dots is the same, right? And it's, again, every 1 second. But then from 4 to 8 seconds, right, the car is slowing down. Well, what if I said, well, I want to know, I just want to analyze the car slowing down, the car coming to a stop. Well, then if that's the case, then we're not worried about all of these dots. We're going to start everything relative to here. So then this will be our origin. This is our time 0. So again, it kind of, even though you have all this other stuff, you don't really worry about that because we're only going to analyze the car braking. And so that's why we're analyzing these last 4 seconds. Okay, so with time, you have to be wary that depending on, what motion you're analyzing, because we got 2 kinds of motion here. Right? From 0 to 4 seconds, it's moving in a constant speed. It's that uniform motion. And then from 4 to 8 seconds, it's slowing down. All right? And it's decelerating, so to speak, which we'll talk about later on. So a change of position is called displacement. And we talked about this. This is kind of a little review. We talked about displacement, how far you are from where you started. So if you look here, x sub I, that's going to be my initial position. X sub f, that's going to be my final position. So if I start here at 50 and I end here at 0, I went to the left. So my answer is going to be negative. So if you look at the difference between the two, this delta means change in, right? So a change in x. So that's going to be x final minus x initial, final minus initial, my change, that delta means change in. My final position is 0. My initial position is 50. So it's going to be 0 minus 50, which is just negative 50. So when you think of the negative sign, don't think of it like you did in math, where, what that means. In physics, the negative sign tells you a direction. Okay, so it tells you it's not like you lost 50, 50 feet or whatever. That negative sign is just telling you reference to where we measured it, right? It's to the left. So keep that in mind. In order to quantify motion, again, we got to consider also some time intervals. So in other words, again, talking about initial and final position. So this is my initial position. This is my final position. All right. And at my initial position, I was at 0 seconds. And then at my final position, I was at 6. So my time interval is your final time minus my initial time. Well, my final time is 6 and my initial time is 0. So my change in time, so to speak, is 6. And then my change in position, again, if we go back to this, right, a change in position, that's your displacement. So my displacement here would be 120. It's my final minus my initial, which is 0. So it's just 120 minus 0. So my position or my displacement is 120. My time, my change in time is 6 seconds. And that's kind of what I talked about here. So I'm going to go ahead and move on. All right, so how long a ride? So Carol is enjoying a bicycle ride on a country road that runs east and west past a water tower. Define a coordinate system so that increasing x means moving east. So they're just kind of wanting you to note again that like if we're going towards the right, those are your positive x values. So this is my coordinate system, is the x. This is going to be my origin. So anything this way to the right of my origin is positive. To the left of my origin is going to be negative, okay? Because it's to the left of where I started. So at noon, Carol is 3 miles east of the water tower. At half hour later, she is 2 miles west of the water tower. What is her displacement during that half hour? Okay, so let's think about this, right? We are here. That's our start at 3. And then our end is -2. Okay, that's our end points. We want to know what is her displacement during that half hour. So if we go to the next slide, all right, Carol is moving to the west, so we expect her displacement to be negative, right? Because she's going this way. She's going to your, if you're looking at the screen, to the left. We can see from our picture that she has moved 5 miles from her starting position. So, I mean, if you think about it, she starts here and she ends here. So if you go from here to here, that's 1 mile. There's 2 miles. This is 3, 4, and 5. So her distance is 5 miles, okay? But then I want to know, okay, well, it's 5 miles what? It's 5 miles to the left. All right, so you can see we can actually even mathematically calculate that. So her final position, again, if we're measuring it from our origin, her final position is that -2 minus, because it's delta x, which is that change in distance, change in displacement. Her final or her initial is 3. So if we subtract those, we're going to end up getting a -5 miles. And again, that's just telling you relative to her starting spot, she's 5 miles to the left of that. Maria is at position x equals 0. She then travels a distance of 70 meters west and then comes back 30 meters east. What is her displacement and what is her distance? Okay, so Maria's displacement, remember, displacement is how far you are from where you started. So if we start at the origin, and her displacement is how far she is from where she started. So she traveled 70 meters, and then she came back east 30. So she ended right here. So how far I am from where I started, her displacement is just this blue arrow. So that would be our 40 meters, and she would be 40 meters east, okay, or 40 plus 40 meters from where she started. Then what is her displacement? Well, her distance traveled. Well, that's just her total distance traveled. She traveled 70 meters and then 30. So her total distance there for part B is going to be 100. And you don't have to have any kind of direction. It's just going to be 100 meters, by the way. All right. Now, we're just about done here. I've got a few more slides. But like I said, this is kind of getting us into this physics. And a lot of the stuff that we're talking about today, these words are going to be talked about throughout the entire year. And particularly these are called vectors and scalars. And I don't know if you've ever heard of these, and we'll kind of visit these again next week. But vectors and scalars. So a quantity with both magnitude and direction is called a vector. A quantity that has only magnitude is called a scalar. So really a vector is a scalar with direction, okay? So if I go back to this slide here, right, and I say displacement, I have to have a direction with displacement, right? Displacement is she was 40 meters east of where she started. But for B, we just said her distance traveled was 100. So it didn't matter her distance, or excuse me, her direction. So for B, that would be a scalar. And then for part A, the displacement, that's a vector because you have to have a direction. And so vectors, all of these are vectors, which means they all require some type of direction. And then scalars do not. Distance, speed, and time, it doesn't matter about direction at all. So they're just quantities that have magnitude. And magnitude is the size of something. Have you ever heard like the magnitude of a earthquake or something like that? It's how big it was. Well, that's what a scalar is. And sometimes in problems that you'll read, they'll want to know, well, what was the magnitude of her displacement? What was the magnitude of her distance? That's just asking for, or magnitude of displacement, that's just asking for the distance. Okay, we don't care about the direction. So anytime you see magnitude, it's just the answer. That's all they're wanting, is just the answer. You don't have to worry about a direction at all. So with our vectors and scalars, we have to have we have speed and velocity. So it's not okay. So we have like we have distance, displacement, we have vectors, we have scalars, we have speed, and we have velocity. So if I go back to the previous slide, you can see that a vector is velocity, or velocity is a vector, and speed is a scalar. So that means then that speed doesn't have to have a direction. Speed is just how fast you're moving. All right. Velocity, though, requires a direction. So it's how fast and what direction. So if you're going 55 miles an hour, that is your speed. But if I say 55 miles an hour north, then that is my direction. And therefore, that would be my velocity. Okay, so when you add a direction, then that becomes velocity. Motion at a constant speed. So we mentioned constant speed towards the beginning of this lecture, and I just wanted to reiterate that constant speed in a straight line is called uniform motion. And again, that means you're covering the same distance in the same amount of time. Okay, and so we have an equation here, speed. Speed is distance traveled divided by time. Speed is the total distance you traveled divided by time. So like, for example, if I talk about speed at the like Indy 500 or the Brickyard 400 or something like that, sometimes those different races last a couple hours. Well, Indy 500, you're going 500 miles, and it may take 2 hours to hit those, or 3 hours to do those 500 miles. Well, total distance traveled, 500. Total time, 3 hours, and you divide that out, and that would give you your speed, or the average speed, I should say, for that race. All right, so just kind of think about that. We're gonna be focusing more on speed and velocity here as well. All right, straight line motion. So again, we're talking about uniform motion, talking about constant velocity. Again, you're covering, if you look up here, you're covering the same distance in the same amount of time. That's why those arrows are the same, because those arrows are representing the velocity, because arrows are what you use to represent vectors, and velocity is a vector. And again, we'll get more into that. I'm just kind of introducing that to you. We'll get more into that next time. And then here is a graph, and we're going to do some graphing this week. Just basic stuff here. We have a distance time graph, and I'm plotting, that you can kind of see that at 1 second we're here, at 2 seconds we're here, at 3 seconds we're here. So you can kind of see that we're covering, again, the slope here would be the same. And so this is a distance time graph. And so the slope of our distance time graph tells me the velocity, tells me how fast we're moving. And so that's something that we're going to look at in the lab next week. We're going to be looking at a velocity time graph, or this week, we're going to be looking at a velocity time graph, or excuse me, position time graph, and finding the slope of that. And that slope should give you how fast the car is moving. Now this, keep in mind, this is not that the car is accelerating, it's moving at a constant speed. Okay, so again, speed measures only how fast you're moving. Velocity tells you the direction. So for velocity, it's displacement over time. So again, you can see the bike is moving to the right. Here, the bike is moving to the left. So they could have the same velocity, just one might be negative and one might be positive. Okay, because again, one's moving to the right and one's moving to the left. So velocity is displacement over time. All right. Now the last couple things here, I kind of just mentioned this too, I guess, in the last graph, but when we have a straight line like this is length and mass, which it doesn't matter, but it's a straight line. I just want you to understand that, you know, this relationship is this equation, your slope-intercept form, y equals mx plus b. So if I go back to this graph here, right, this line is y equals mx plus b. And b is usually, of course, 0 because it goes to the origin. And then m is your slope, and then x would be whatever's your measuring on your x-axis, and then y is what you're measuring on your y-axis. And then, of course, slope is rise over run, but again, we always do, you know, y2 minus y1 over x2 minus x1. I mean, if your slope is negative, right, then if y gets smaller and x gets larger, then that's going to be a negative slope. All right, and so we're going to be looking at more graphs and stuff and reading graphs later. I just wanted to get you into, and let me go back to this. I just wanted to get into this kind of graphing because this is what we're going to be using in our lab, is a position time graph and the slope. Okay, the last thing here is we have a bicycle is moving to the left with increasing speed. Which of the following motion diagrams illustrates this motion? All right, so we have 4 graphs. These diagrams, those arrows are just showing you the direction. They could be your velocity vectors, and they're showing you that you're moving to the left. So a bicycle is moving to the left with increasing speed, so you're going faster. So if you're going faster, think about those arrows. If you're going faster, the arrows should be getting bigger. So let's see, which one is it? The answer would be B. Very good, right? Because we're moving to the left, so the arrows are going that way, and we're going faster, so those arrows should increase. Okay, so that's it for today. I might be adding another one up here. I'm not really for sure yet. We'll kind of see how things go. But I just wanted to, again, state and kind of go back to the beginning. I'm going to fast forward here, fast backtrack, I guess. But I want to just kind of go back and review, again, that we were analyzing the motion of an object, and we looked at that motion using these motion diagrams, which is what we're going to be doing in the lab here this week. And then also looking at position, displacement, speed, and velocity, and how those all relate. So thank you, and I will talk to you soon.